Good morning, good afternoon. I'm very happy to introduce our work on monitoring groundwater pumping using electric energy as proxy in a pilot area in the North China Plain. This work is done in cooperation with the local water authority. So this is the content of my presentation. I will first introduce the features of groundwater pumping in the North China Plain and also the pilot area of Guantao County. Then I will introduce the key technical component of this monitoring method, conversion from electricity to water. And then I will introduce how we collect and pre-processing electricity data. Finally is the application. So groundwater pumping in the North China Plain, the features can be seen from this picture. You see the green crop is winter wheat because there is a little rainfall in winter and spring in the North China Plain. Irrigating winter wheat is the main reason of groundwater pumping in the North China Plain. And you see this is a well, a typical well in the North China Plain. We don't see the pump because it is the submersible pump that is in the tube of this well. Water is pumped and conveyed by this flexible pipe to the field. The locals call it little white dragon. And there are all these pumps is motored by the electric energy. You see here is a electrical transformer that supply power for the pumps. There are many, there are a huge number of small scale wells with a very primitive condition of wells like this in the North China Plain. You see there is no water metering at these wells because it is very difficult to install water meters and at the same time very difficult to maintain. So we try to monitor groundwater pumping by electric energy. This is our study area, the Guantao County. It locates in the south of the North China Plain, also the south of Hebei Province. And there are about 8,000 irrigation wells in this county. There is no water metering at the wells, but the electric consumption of each single well is metered for electricity fee collection. Since 2017, the local authorities start to collect water tax. So the groundwater abstraction data is needed for a yearly step. Among those 8,000 wells, most of those wells are the shallow wells that pump water from the shallow unconfined aquifer with the depth to groundwater table around 20 meters. There are more than 7,000 shallow wells in Guantao County. There is also some wells that pumps deep water from a deep confined aquifer with the depth to groundwater table around 70 meters. And the irrigation area per deep well is quite larger than the shallow wells, but the number of the deeper wells is much smaller than the shallow wells. Since 2014, large amount of surface water is imported to Guantao by the main canals. And there is irrigation areas that can be covered by the surface water along the canals. It is within 1 kilometers along the main canals. Because the main wells are the shallow wells, our work focus on the shallow wells, electricity to water conversion. We also need to know the depth to groundwater table because it influences the electric energy used to pump per unit of water. You see there is a long-term decline in groundwater table, both in shallow and in deep. Since 2000, the decline rate of the shallow water level is not so fast, but still there is a seasonal variabilities in the water level within a year for the shallow wells, for the shallow aquifer. You see during the pumping seasons, the water level goes down quickly, and then in non-pumping seasons, the water level goes up due to the recharge from rainfall. Now I will introduce how we convert electric energy to groundwater pumping. We try to use a simple conversion factor for the sake of easy implementation. We introduce this electricity to water conversion factor in the unit of cubic meters per kilowatt hours to convert electricity consumption to water volume. And this should obey the law of energy conservation, meaning the electric energy is consumed for the gravitational potential energy of the water, and also a lot of energy is lost during pumping of the water. By equation, it can be written as the power is a function of discharge, also, or electricity is a function of water volume pumped. And this conversion factor can be written by this function. So the influential factors includes pump efficiency. It's not only the shaft efficiency of the pump, but also the motor's efficiency. Also the depth to groundwater table and additional drawdown during pumping, and the head losses along the pipe determine the lift of the pump. So they are also the influential factors. One would say that I know the nameplate of the pump, then I adding these values into this equation, then I can calculate the conversion factor. Yes, that is correct, but the values given by the nameplate and the characteristic curve of the pumps is the rated values, meaning it is the values at the optimal working function of the pump. In reality, the true values can be deviated from these rated values. So what we solve this problem is to do the pumping test in the field. We measure the flow rate of a well by the portable ultrasonic flow meter or by the volumetric method. And we read electricity meter and record the time using stopwatch correspondingly to calculate the power. Then we can get the conversion factor of one well. At anywhere it is possible, we also measure the depth to groundwater table using dipper. It is for deriving the pump efficiency. According to our experience of a pumping test, we give some suggestions on how to do the pumping test. This is the equation of a calculation, discharge divided by power. We recommend that the measurements should be done during pumping. That means at least 10 minutes after pump is turned off, because in the first 10 minutes, the water level in a well will drop down drastically. The measurements can only be measured when the flow is steady, which is at least 10 minutes in Guantao case. In other areas, this time could be different. And for the wells with rough pipe conditions, we recommend these mechanical flow meters that can be attached to the outlet of the conveying pipe. For the wells, for example, the deep wells, which have the relatively good pipe conditions, we recommend the portable ultrasonic meters to measure the flow rate. For measure the power, because the pumps use a three-phase electric power. Some electricity meter in the field only measure one of the phase, so one needs to be careful whether this meter measures one phase or three phases. If it only measures one phase, the measurement should times 3. And for the accuracy of power measurement, one should wait at least 5 minutes or let the electricity meter run for at least 3 kilowatt hours to make sure the power calculated is accurate. Also, we recommend these self-made dippers to measure depth to groundwater table because it's very cheap and you don't need to worry it's stuck in under the well. This is the pumping test we have done in Shoushansi district. This area, all the wells are shallow wells, and the color of the different colors of these dots showing the wells tested at different time. There are in total 281 wells tested in this area. And we also surveyed more than 500 wells to get the pump information and other irrigation related information. In the whole county area, we also did the pumping test for both shallow wells and deep wells. So this is the results of the pumping test. The size of the dots represent the value of a conversion factor of the well. You see there is large variations in values from 1 to 4 cubic meters per kilowatt hours. The correlation we found there is a positive, correlation between conversion factor and pump rated power and depth to groundwater table. In this table, you can see that the more powerful the pump is, the less water it can pump using the same kilowatt hours of electricity energy. And the pump efficiency we could calculate based on the conversion factor and the lift we tested. It is around only 70%. This is much lower than the rated values given by the nameplate of the pump, which is usually around 50 to 60%. So that was the pumping test to determine the conversion factor of many single wells, but it can only be done in one specific time. To know the temporal variability of the conversion factor within a year, we installed smart meters at 6 wells, and these smart meters transmit water volume and electric energy at the frequency of once per hour to our server. So it is like we do the pumping test every hour. But this method is very difficult to maintain because we need to do a lot of efforts to avoid tampering and theft. Also, there can be hardware malfunction that will influence the data we get. So this is the result. The location of these 6 wells is also in Shoushansi district. And the figure in the middle is the measurements from 2 wells. You see there are 2 groups. Due to the hardware malfunctions, the upper groups have to be excluded because the flow rate of these points is unrealistic for a shallow well. if we look at these values of good quality, we see that the spread of these values is generally within 20% of the yearly mean value. If we look at the other 4 wells, also, all the 4 wells, the spread of hourly conversion factor is within the 20% of the yearly value. This means in whichever irrigation season we do the pumping test, we could get a conversion factor of the yearly value with the accuracy of 20%. If we look at one of the measurements of the wells over time, this is the conversion factor, the gray dots. The red dots are the moment when the pump is turned on or off due to the peak of electric energy. These are outliers during pumps is turned on or off, and they should be excluded. So we only look at the gray dots. And we can see that the gray dots varies with the variability of groundwater level. For example, in June, the water level is very low and the conversion factor is also very low. And there we found, if we look at the conversion factor per unit, we derive a negative correlation between the conversion factor and depth to groundwater table. This is very important, and because this is the basis for us to estimate conversion factor using depth to groundwater table. So let's talk about the accuracy of the conversion from electricity to groundwater pumping. As mentioned before, the pumping test can provide the measurements with the error less than 20%. This is depends on the seasonal variability of the depth to groundwater table. In extremely dry years, the depth to water table could be very low, which might drastically decrease the pump efficiency. So we suggest to do additional tests in extremely dry years to take into account this situation. And in areas where there is long-term decline of water level, the periodical test should be performed once every 1 or 2 years, depending on the decline rate of the water level. The accuracy at single wells, as the spread of the conversion factors among single wells is quite large. If we use a uniform conversion factor, say the average conversion factor, then the errors of the conversion can be up to 60%. So we recommend to do pumping test at each single well to maintain the accuracy within 20%, or at least the pumps should be grouped by the rated power, and the selected wells can be tested with the typical rated power pump. If we look at the accuracy at county level, maybe there is no need to do all pumping tests at all wells to obtain the average conversion factor of an area. So the accuracy of conversion at a county level is actually determined by the number of wells tested. We look at this in details. So it can be formed as a question: how many wells in the county should be tested to obtain an average conversion factor with a relative error less than a threshold, for example, 20% for water tax collection? This problem can be solved by the theory of interval estimation. This statistic obeys a t-distribution, so the minimum required sample size can be calculated by this equation. In a simple word, the required minimal sample size is actually determined by the coefficient of variance of a conversion factor among wells, which means if the spread of conversion factors among wells is large, then more wells should be tested. This table gives the required minimal sample size for 4 villages and for Shoushansi districts. You can see that if we would like to achieve an accuracy of 20%, we do not need to test all the wells, only less than half or around 1/3 of the total number of wells in a village. And if we would like to achieve higher accuracy, for example, 10%, then it's about half, or in some villages, all the wells should be tested. The case in Shoushansi district, the total number is 600. You see only 14 wells needs to be tested to obtain an accuracy of 20%. We think that the spread of a conversion factor among wells is in the Shoushansi district is representative of the whole Guantao County. So to obtain the average conversion factor of Guantao County, at least 14 wells should be tested to reach the accuracy of 20%. In the whole Guantao County, we chose 17 wells that are evenly distributed in the county. And we calculate the average conversion factor is 2.62 cubic meters per kilowatt hours. If we compare this value to the local authorities' conversion factor, the difference is around 20%. This is mainly due to the difference in number of tested wells. They only calculate this value from 5 tested wells. And we also did pumping test at deep wells and the surface water pumping station. Due to the difference in pump lift, you see the conversion factor of deep well is about half of the values of the shallow wells. Well, for the surface water, because the lift is only around 8 meters, the conversion factor is quite large, 13 cubic meters per kilowatt hours. This means when we do the conversion from electricity to groundwater pumping, we need to identify the sources of water to use the correct conversion factor. Now I will introduce how we collect the electricity data and how we process those electricity data. This is a monitoring system of pumping electricity in Guantao. The Guantao Department of Electricity and Power Supply is in charge of pumping electricity management of the whole county. And there are 11 districts of a sub-district of the electricity management department, and it is divided according to the location of townships. In each of the district, there is several villages, around 20 villages. In each village, there is one electrician who is responsible to maintain the electricity infrastructure and also collecting the electricity fee. In each village, there are several transformers that supply power for the pumps. And at each wells and the electricity use of the pump is monitored by electricity meters. Before 2018, these traditional electricity meters with farmers' self-records. And since 2018, the monitoring system is upgraded. At each single well, there is a smart meters with data transmission with the frequency of once per day. We got the monitoring electricity data mainly from base level, from the well level. So for water resources tax collection, the single well's yearly electricity records is the data we have got. And for reconstruct historical groundwater pumping, we also collect the electricity consumption for agricultural use, which is the total use of the whole Guantao County. And from the statistical yearbooks, we collect the annual rural electricity consumption. All this electricity data have to be processed because there is a non-pumping electricity included. For example, the agricultural product processing factories or the animal husbandry. Also, we need to identify the sources of irrigation water because the conversion factor of shallow wells and deep wells are quite different. So I will introduce how we process this data one by one. First is the single wells yearly electricity data. Looking at this histogram of electricity consumption of single wells, we see most of the electricity consumption of wells is less than 5,000 kilowatt hours per year. This is the electricity consumption of a typical shallow wells. For deep wells, it can be larger. But we also find that there is quite some users that consume more than 40,000 kilowatt hours per year. And we we speculate this electricity consumption as non-pumping users because one can calculate the maximum yearly electricity consumption of a well by based on the estimate of water use per irrigation area and the irrigation area per well and the conversion factor. Beyond the threshold should be taken as the non-pumping electricity users. We can also identify the pumping users by the irrigation area per well because the deep wells generally irrigate larger area than the shallow wells, and also the location of the wells. We generally know the where the deep wells are distributed, and also where the area can be covered by the surface water. There is also one situation that have to collect the information from the village electricians because in some wells, in some villages, several wells is metered by 1 meter. This means we do not know how much electricity consumption is per well, and the total of those wells electricity consumption can be much larger and can be taken as a non-electricity consumption. So this information has to be collected from the electricity department. For the agricultural electricity consumption, we need to exclude non-pumping electricity as well. We can look at the monthly time series of this agricultural electricity consumption. In non-irrigation periods, for example, in January or generally in the winter seasons, we can take them as the non-pumping seasons, and the electricity consumption in this month should be excluded as the non-pumping electricity. For the rural electricity consumption, not only the animal husbandry and the agricultural products processing electricity consumption are included. Also, the domestic use electricity consumption are also included. So we make an assumption, we assume that the electricity consumption for the non-pumping users grows smoothly with time as the economy increase, and the interannual variability of rural electricity is caused by pumping electricity, which means it is the randomness of annual rainfall. So if we have the annual time series of rural electricity consumption, we could do detrend, using the detrending method to extract the interannual fluctuations of the time series and apply these interannual fluctuations to the estimate of average pumping electricity to get the time series of pumping electricity. The other method is that we can estimate the non-pumping electricity consumption by the GDP, the gross domestic product, as an economical index. And by excluding this part of estimation from the total rural electricity consumption, we get the pumping electricity. Now, here comes how we can use this monitoring method and where it can be applied. First, we assessed the feasibility of the monitoring method using electricity as proxy. We compared this monitoring strategy with the direct water metering strategy. And for this indirect metering strategy, we considered two methods. One is the pumping test at all wells, or the pumping test only at the selected wells. We assess these strategies in 4 criteria. First is the cost. The second is ease of implementation, and the third is accuracy and the equitability of this using this method. You can see that using a direct water metering system, the cost is much higher than using the indirect metering method. This is because it not only required investment in installing water meters at the wells, but also required the maintenance efforts to make the water meters run optionally, to run functionally. Well, for the indirect metering strategy, we only need the cost for doing the pumping test. Taking an example of the water tax generated in 2018, you see that this amount of money is not affordable for the cost of direct water metering, but it is affordable for at least more than 2/3 of the wells to be tested in Guantao County. And regarding the implementation, we have faced many difficulties in making the water meters run. But for the direct metering strategy, the electricity metering system is well maintained by the electricity department, and doing pumping tests is much easier than maintaining a water meter. Regarding the accuracy, if the water runs work functionally, the accuracy is high, of course, but the electricity method will provide the accuracy around 20%. It is relatively lower than the direct water metering strategy, but it is still acceptable for water tax fee collection. If the pumping tests can only be done at a minimum number of wells, then the accuracy can be very low, larger than 50%. But if we look at the whole county, the accuracy is still acceptable, is around 20%. The equitability is related to the accuracy, meaning whether the farmer is charged for the real water volume pumped. If the for the direct water metering, the accuracy is high, so it's equitable for the farmers. If we do the pumping test at every well, we get an accuracy within 20%. It is also fair for farmers to pay. But if only a minimum number of wells can be done, then for farmers at single wells users, they might pay more or less for the extra water they really pumped. But from the energy saving point of view, it is fair, because the farmers using inefficient pumps used more energy, so they are punished for this. So we think the strategy of using electricity as proxy to monitor groundwater pumping is sustainable regarding the cost and implementation efforts, and also it provides acceptable accuracy. So this is the application of this monitoring method in determination of water tax in Guantao County. Since 2017, the local water authorities determined water tax using this monitoring method. On the figure on the left, you can see the water consumption of each village, and on the right figure, you see the water consumption of each township. We can clearly see how much water is pumped from the shallow aquifer, and how much is pumped from the deep aquifer, how much is pumped from the surface water. And by drawing a quota for water tax collection, one can clearly see on average which township is using more water. And the similar figure can be done for each village for the water tax collection. Since 2018, all the electricity meters at single wells are upgraded to the smart meters, so it provides the possibility to monitor groundwater pumping by real time. Also, the electrical transformers electricity meters are also smart meters with the data transmission. All the meters are transform data at the frequency of once per day. So we propose an innovative monitoring method based on the smart electricity meters and transformers. Because one transformer supplies power for more than one wells. When there is one pump turned on, you can clearly see a jump in the power measurements of the electricity meter. And we can clearly see multiple pumps is turned on or off by looking at the power measurements over time. And all this data are transmitted to our servers, and we can use this data to analyze which data points belong to which pump by using the machine learning techniques. At the moment, these techniques works well for simple cases. And provided by more data, we are very confident to use this method to identify the multiple pumps working conditions. This method can be used in areas where there is no electricity meters at single wells, but there is electricity meters at the transformers. In areas where electricity meters is installed at every single well, we can obtain the daily electricity consumption of these single wells. Again, also the machine learning techniques can be used to identify the user's type of these wells. For example, which is only wheat and maize, and which wells also irrigate greenhouses. And by the preliminary analysis, the features can be captured based on the frequency and the daily consumption of this electricity use. This method can be applied in areas where there is mega data of pumping electricity at single wells, while there is not enough information to identify the users. The other application is reconstruction of groundwater pumping in history. Because there is historical electricity records, so we can convert these records to groundwater pumping in history. But one thing has to be kept in mind is that you see there is an increase of electricity consumption over time. It doesn't mean that the pumping electricity increase in time. It can be. It doesn't mean that the groundwater pumping volume is increased over time. It can be caused by the decrease of water level, because more energy is required to pump the same amount of water. So to solve this problem, we can estimate the historical conversion factor using this equation. The pumping efficiency we get from the pumping test. The depth to groundwater table we have is also measured. We have the records. The drawdown during pumping can also be measured, and the head losses along the conveying pipe can be calculated, or it can be neglected because in Guantao, in many cases, the flexible plastic pipe is used. There is very little head losses. So using this equation, we can calculate the historical conversion factor. And using this historical conversion factor, we got the historical groundwater pumping records. The same equation can also be used for the estimation of a conversion factor within a year. I mean the seasonality of the conversion factor if we have the change of water level within a year. So these results can be served as inputs of groundwater models. And the 2D groundwater model will be introduced by Dr. Li Ning tomorrow. And I will also introduce the box model for Guantao shallow aquifer using the converted groundwater pumping records. So in summary, groundwater pumping monitoring using electricity as proxy has many advantages. It has the records of electricity data is relatively objective, and the conversion from pumping electricity to groundwater abstraction is simple, and also the conversion provides acceptable accuracy. Because the electricity monitoring system is well maintained by the electricity department and it is protected by law, the monitoring method is sustainable and the cost is very cheap. Using the historical electricity records, we could reconstruct the pumping in history. Also, we can also achieve real-time pumping monitoring by the real-time electricity, smart electricity meters. There is also challenges by using this monitoring method because this requires the close collaboration between water department and electricity department. This regards the data and supportive information sharing because for the electricity department, they only care about how much electricity is consumed for fee collection. But for water department, the additional information like pumps type, well type, and irrigation areas are also required. So this information should be shared by electricity department. Also, when doing the pumping test, the assistance from the local village electricians are very important. The electricity department also play a role in fee collection. With the close collaboration between water department and electricity department, we believe this groundwater pumping monitoring using electricity as proxy should be work well in the whole North China plan. So this is my presentation, and you can contact me by this email. Some of the information introduced in my presentation is published by a recent paper. And thank you for your time.